Hello guys, and welcome back to Introduction to Number Theory. This time we will discuss a theorem which is about figures on planes. This theorem itself, it's not about prime numbers or divisibility or remainders or anything like it. But in a really astonishing way, it can be used to prove facts about prime numbers, divisibility, remainders, and so on. It's called Blichfeldt's theorem or Blichfeldt's lemma. We will use the word lemma because it is an auxiliary fact. So the Blichfeldt's lemma, and it states that if we have a figure on a plane, and it can be just any figure as long as it has area, so let f be a figure on the plane, and suppose that area of f is greater than n being a positive integer, then there exists a shift of this figure. Well, this is capital Greek letter phi. So there exists a shift phi to, say, phi prime. It's just a parallel shift such that phi prime covers at least n plus 1 points with integer coordinates, which are also called points on the integer lattice. So there exists a shift phi to phi prime such that phi prime, this figure here, not phi but phi prime, covers at least n plus 1 points with integer coordinates, or we can call them integer points or nodes of the grid or nodes of the lattice. All these are synonyms. So at least n plus 1, well, let's call them nodes. Now let's prove this theorem. For this purpose, I will draw the lattice. And some figure on it. It will be not a regular figure, but it will by all means have an area. We'll say something like this. Or something like this. And we know that the area of this figure, well, this is our figure phi. We know that the area of this figure phi is greater than n. So to prove that there exists such a shift, we need to cut this figure along lines of the grid. So we cut the figure along this line and also this and this and this, and it falls apart into small pieces. First piece, second piece, the third piece, fourth, and even fifth, but this is only for this particular figure. Another figure can fall into more pieces. The number of these pieces can be infinite. It doesn't matter actually. And now we have all these pieces so we have cut the figure into pieces along the lines of the grid. And now collect all these pieces in one of the squares of the lattice. In any of them, choose, say, this one, and we collect them also using the parallel shift. So we mustn't turn them around, we mustn't flip them, just the parallel shift. So this one piece here will go over here. This is piece number 1. And this one piece here, this one piece here will be shifted over here, something like this. This is piece number 2. This one here, rather big one, will be shifted, well, it's just a parallel shift over here. So we'll get something like this and this. And this already starts to look like a mess. Well, it sure is. And piece number 4, we'll collect all these pieces into one square of the lattice. Piece number 4 is something like this. I know it is impossible to follow all these pieces in one square, but it doesn't matter. Well, this is piece number 4, and piece number 5 is somewhere over here. Piece number 5. So, okay, so we've collected all these pieces in one square, but for what purpose? Well, we understand that area of our figure initial is greater than n, but area of one square is equal to 1. So we understand that all these pieces, all these small parts of our initial figure, the sum of their areas, well, we can denote these pieces F1, F2, and so on. These are pieces or parts of our figure, phi, and areas of these parts, well, we don't know the exact number, so areas of these parts are equal to the area of our initial figure phi, which is greater than n, which is n times greater than the area of this square. So from the geometric pigeonhole principle, it follows that there exists a point in this square, well, somewhere inside it, which is covered by at least n plus 1 pieces or parts of figure phi. So let's denote this point P. And this point P is covered by at least n plus 1 parts. Which means that if we now return all the parts to their places, this point P will have corresponding points in at least n plus 1 parts. So we have n plus 1 parts here that cover point P, and when we take a look at the original figure and where these parts were here, we will see that there is a point in every of these parts that corresponds to point P. So say, well, this point here corresponds to this one, call it P1, and also to this one, call it P2, and so on. So we will have points P1, P2, and so on. And we understand that there are at least n plus 1 such parts, so there are at least n plus 1 such points. And the main thing is that all these points here correspond to the same point in this square. Do you know what this means? This means that if we shift our figure by a vector that connects this point P and one of the vertices of this square, then by shifting our figure to this vector, by this vector, it will cover n plus 1 integer points. So here it will look like something like this. So all these points that corresponded to P after shifting coincide with some integer points. So the figure, when shifted by this vector, will cover n plus 1 integer points or n plus 1 nodes. So this finishes the proof of Blichfeld's lemma.